Okay, we ever take another integral. This one's from MIT Integration Bee, 1991, number 40. We have the integral of square root tan x dx. Okay, this is one I actually did before. I just wanted to go back and revisit it because I just thought it was such a good problem. Okay, now to get started with this, I do know a few different ways to do this, and I'm going to do the more straightforward method in this case. I'm going to do just a u substitution for the whole thing. There is a trick you can use, and I'll bring that up at the end of the video and show how that works. But right now I'm just going to do this for a u substitution. And then before taking the derivative, let's solve for x. So squaring both sides, we're going to have u squared is going to be equal to tan x. Then take arctan on both sides, and we have x is going to be just arctan of u squared. Take a derivative here to get our dx value. This is going to become 1 over squaring this, we're going to get u to the fourth plus 1. Then chain rule on this is going to bring a 2u into the numerator. So now I'll go ahead and substitute it. All this stuff here is just going to become a u, and then we're going to have our dx value. It's going to be 2u du over u to the fourth plus 1. Well, I can take the 2 out front of the integral here, and u times u is going to be just a u squared. And then what we have here is another integral I've done before. This is actually kind of a tricky one as well. Even though it doesn't look that bad, it's a little hard to deal with the fourth power here and with the square part in the numerator. What I want to do to try to clean this up is let's multiply in 1 over u squared and do the same thing in the denominator, so we're just multiplying by 1. When I do this, it's going to become, in the numerator, it's just going to become like 1 du. The denominator is going to turn into u squared plus 1 over u squared. Now the interesting thing with this denominator right here is I can factor it a couple different ways. I can do u plus 1 over u. When you square that out, you get u squared. You're going to get the 1 over u squared. The middle terms are going to create a 2, so we don't want to change it, so we'll write it like this, squared minus 2. And then the other way to do this, we can take u minus 1 over u. Same kind of thing, squaring it out, you're going to get the u squared, you're going to get the plus 1 over u squared. The middle terms create a minus 2, so I'm just going to add a 2. So both these are equal to each other and equal to this. So what I can do is I have my choice. I can write the denominator this way or this way. And so what I'm going to do is actually create two integrals, one with this denominator, one with this denominator. And then we just have to kind of figure out how this is going to work to try to set up a substitution. Okay, so now that I have this broken up, you'll see I've got my numerator. I just left it blank because I don't know what I want to do there yet. I'm really trying to set this up for a substitution. Like what I want to happen is I want to do a substitution for this. Because if we do a substitution here, this is going to be kind of like our arctan formula. This is also going to work kind of the same way, so we're going to want to do a substitution for this. So like let's start with this one. We'll call this t, and I want to do a substitution where t is going to be equal to u minus 1 over u. Take a derivative, so the dt value is going to be 1. This is going to become plus 1 over u squared du. So we're not sure if this is going to work yet. I'm just kind of forcing this to happen. I'm going to have to check because we don't want to change it, right? Our numerator here should be like 2 times 1. Just going back to our problem here, when we put everything together, the whole numerator together should just be 2 times 1. So for now, we're just going to set this numerator like this. And then let's do the same kind of thing over here on this one, calling this v. So I'm going to say v is going to be u plus 1 over u, and then dv is going to become just 1 minus 1 over u squared du. And so then we'll come over here, we'll force this one to happen as well. We'll do just the sign change, 1 minus 1 over u squared du. And the reason this is going to work, you notice if you multiply everything out, the 1 over u squareds, well, 2 over u squared when you multiply in minus 2 over u squared, those are going to cancel and that part goes away. If we add up the whole numerator here, we're going to get 2 times 1 here plus a 2 here is 4. We want this to be a 2. All I need to do to make this work, if I just remove these 2's, and so this is going to work, this adds up to the same thing as this, these are equal, just looks totally different. So from here, we'll just go ahead and substitute this. Again, this being our t, so this is going to become, everything in the numerator is just dt, and this is going to become t squared plus 2. But for plus 2, let's write this as square root of 2 squared, just trying to set up the formula for the, just trying to set up our arctan formula here. Then for the next one, really similar, this is going to become v squared minus, we'll do the same kind of thing and write this as square root of 2 squared. And the numerator is just going to become this dv. Well, then at this point, this is perfectly set up for our arctan formula, and really similar, this one is set up for our inverse tanh formula that we can use on this. So just going ahead with this is going to be our a value in the formula, so that comes into the denominator. So we're going to have 1 over square root of 2 arctan of t over square root of 2. And this one's less familiar, but really the same kind of thing. It's going to be minus sign coming out 1 over square root of 2 inverse tanh in this case, and it's going to become v over square root of 2. And so now all that's left to do is we just need to back substitute in order to finish this thing off. Now before I do this, just to save a step, let's get it all the way back to x, because if I substitute back in for t, we have in terms of u. So the way I can do this, we have our u value right here, but we're going to want a value for 1 over u. That's just going to be the reciprocal. That's going to be the same thing as square root of cotangent x. So then using that first for our value of t, this is going to become square root tan of x minus square root cotangent x. And then over here for v, same kind of thing, square root of tan x, but now we have a plus square root cotangent x. And then with these values, we have everything we need to finish it off. Let me bring my solution all the way down here. So this is going to become 1 over square root of 2 arctan. Our t value is now this, so it's going to be square root tan x minus square root cotangent x. Then we're going to have minus 1 over square root of 2 inverse tanh. Then our v value is going to be same kind of thing added. It's going to be square root tan x plus square root cotangent x over square root of 2. Add a plus c, and that's it. And so like you can see with this long solution, it's actually kind of pretty involved considering how simple it looks initially. And then going back to the trick I mentioned before that I didn't want to use in this one, you'll notice how we end up with square root of tan x plus square root cotangent x here. We end up with the same kind of thing subtracted here. Well, doing this problem with the trick, you just kind of set this up initially. Your first step is to add a cotangent x like that, but then you don't want to change it, so you subtract off a cotangent x, and then you still want something more to work with the cotangent x, so you add another tan x over here. So it's kind of a crazy method, but this actually probably makes it a little bit easier because then you're setting it up exactly to get to this solution. So this is something you can mess around with. I did another video with this. I think it was probably the definite integral, but I have done it this way before. Anyway, I thought it was a really good one today from MIT 1991. Thanks everyone for watching. Have a good day.